Hello, I am Rahul Baghel, Assistant Professor, Chhattisgarh Swami Vivekanand Technical University, Bhilai. Welcome you all to the course on Industrial Automation and Drive again. Today we begin with our 21st lecture on Mathematical Instruction based PLC program. In previous lecture, we covered the Star Delta starter and their PLC programming and some logical instructions. In the first instruction, ADD, that is add instructions. As you can see in the diagram, in the first rung, add instruction is connected with the switch I:0/0, and you can see the instruction took two inputs in form of source A and source B and provide one output in form of destination. The address of source A is represented by N7:0 and address of source B is represented by N7:1 and the destination address is provided by the N7:2. Initially, the value of source A and source B is set 6 and 2, right? So the output is 0 initially. In the first case, when switch is in 0 state, means when it doesn't change their state, so output is 0. You can also see in the data files, input is 6 and 2, and when I press the switch I:0/0 or when I change the state of switch, you can see in the diagram, when I changes the state of switch from normally open to normally close, you can see the output is represented by 8 in the data files and the value of the destination address is changed by 8. N7:2 is equals to 8. You can also see in the data files, right? In data files, we can see our data in form of decimal value, binary value, hexadecimal value or octal value, right? Here I am just changing the value in form of decimal. That's why you can see the inputs and output value in form of decimal, right? Previously or in the previous lectures, we can see in the data files the values are in the binary form, right? So don't get confused that in data files we can see the values in form of what we want in form of decimal, octal, hexadecimal, right? Next instruction is sub instruction and it represented by SUB. In these case also you can see it also takes two inputs in form of source A and source B and provides one output in form of destination. The address of source A is represented by N7:0 and source B is represented by N7:1 and the destination address is represented by N7:2. And the data file is also shown in the diagram. You can see the initial value of source A and source B is 6 and 2. So initially when sub instruction doesn't get supply, the output is 0. You can see in the diagram also. And in the next case, when the input is 1 or when the switch changes their state, the sub instruction gets the supply. That's why you can see the output is changes by 4, right? N7:2 is equal to 4, right? Next instruction is MUL instruction, that is multiplication instructions. In these case also you can see the two inputs are there in form of source A and source B and one output in form of destination. The address of source A and source B is represented by N7:0 and N7:1 and the destination address is represented by N7:2. Initially, the initial value of source A and source B, again I am taking 6 and 2. So in the initial case, the output is 0 because the MUL instruction doesn't get the supply. That's why the output is 0. And you can see in the next case, when I provides the supply to the MUL instruction through the switch I:0/0, it outputs changes by 12. That is multiplication of value of source A and source B, that is 6 into 2, 12, right? Next instruction is divide instruction. It represented by DIB. In this case also you can see the two inputs in form of source A and source B and one output in form of destination. Address is also same like the previous instructions, N7 colon 0 and N7 colon 1, and the initial value is also same, 6 and 2 I am using here. So initially the output is 0. You can also see in the diagram the output is 0 because the DIV instruction doesn't get any supply. In the next case, when I provide the supply to the DIV instruction, you can see the output is changes by 3 because the source A is divided by the value of source B. That's why 6 divided by 2, we are getting 3 as the output. So you can see in the data files, the N7 colon 2 is changes by 3, right? Next instruction is SQR instruction. It represented square root instruction. In this case, you can see in the diagram, the SQR instruction takes one input in form of source and the address of input is represented by N7 colon 0 and the initial value I am using is 25 and the destination address is represented by N7 colon 1. Initially, when the SQR instruction doesn't get supply, the output is 0. So you can see in the diagram, the data files, the value of N7 colon 1 is 0. In the next case, when I provide supply to the SQR instruction by the switch I colon 0 slash 0, you can see the destination, the value of the destination address is changed by 5 or the square root of source A, value of source A. So it changes by 5. The square root of 25 is 5. That's why the output we are getting is 5, right? Next instruction is NEG instruction or negative instructions. In this case also you can see it's one input and one output. One input address is represented by same N7 colon 0 and one output address is same, that is N7 colon 1. Initially the output is 0, as you can see in the data files, output is 0 and the initial value of source A is represented by 25. When I changes the status of switch I colon 0 slash 0, the NEG instruction gets the supply and it changes the data files by minus 25, that is negative value of source A. Initial value of source A is 25, that's why the output is represented by minus 25, right? Next instruction is TOD instructions. TOD instruction means it converts the BCD number, convert to BCD number, right? So before going to these instructions, first we will see what is BCD number or what is BCD. BCD stands for binary coded decimal. It is a method of representing decimal number in a binary form. In BCD, each digit of a decimal number is represented by its own 4-bit binary equivalent. As you can see, the decimal digit is represented by the BCD number. The first column is represented the decimal number, second column is represented the binary 4-bit binary number of that decimal bit, and the third column is represented by the BCD number, right? So 0 is represented by 000 in binary also or in BCD also. So in 1 is represented by 001 in BCD and binary, right? So you can see in the table, the from 0 to 9, the value of binary number and the BCD number are same for 0 to 9 bit, for 0 to 9 decimal numbers, right? And the representation is is in 4-bit binary numbers, right? So 0 to 9 binary number and BCD numbers are same in form of 4-bit. After 9 in BCD, 10 is represented by 8-bit, but you can see in the table the binary number of the number 10 is represented by 1010, right? But the BCD number of 10 is represented by 0001 and 000, right? And similarly you can see the binary number of 11 is represented by 1011, but the BCD number of 11 is represented by 001 and 001. And same for the 12 is represented in the binary is 1100, but in form of BCD number it represented by 0001 and 0010. Similarly 13 is represented by 1101 in binary, but in case of BCD it is represented by 001 and 0011, and so on. The 15 is represented by 1111, but in case of BCD number you can see here it represented by 001 and 0101. And similarly you can see for the 16, 17, 18 and 19 in the binary number and the BCD numbers. 16, if we represent 16 in a binary, it represented by the 8-bit binary, and you can see in the table it represented by 001 and 0000, but in case of BCD number it represented by 0001 and 0110. Similarly 17 represented by 8-bit binary, which is equals to the 0001, but in case of BCD number it is represented by 0001 and 0111. Similarly 18 is represented by 8-bit binary 0001 and 0010, but in case of BCD number it represented by 0001 1000. Similarly 19 in binary represented by 0001 0011, or BCD represented by 0001 1001. And last 20 is represented by in binary form 0001 0100, but in case of BCD number it represented by 0010 0000, right? To convert binary to BCD after number 9, because 0 to 9 BCD number and binary numbers are same, as you can see. After 10 the binary and BCD numbers are different. So if we want to convert the BCD number to binary number, simply we just add 6 in the binary number, right? As you can see in the example, suppose we want to convert 12 in the BCD form. So first we write 12 in a binary. So 12 represent in binary, that is 00001100. So convert 12 in a BCD, we add 6, and the 6 in a binary represented by 0110. So you can see in the diagram or in the examples, when we add 6 in a 12 in form of binary, you can see 0 plus 0 is 0, 0 plus 1 is 1, and 1 plus 1 is represented by 0 and carry is 1, and again the carry plus 1 is represented by 0 and again carry is 1. So ultimately we got the final output in form of 00010010, right? So you can see in the table also 12 is represented by, you can see or check, in binary it represented by 1100, but in case of BCD it represented by 00010010, right? So let's take the programming view. In case of BCD instructions or TOD instructions, in the program it represented by TOD instructions. So you can see the TOD instructions take one input and provides one output. Input in form of source A. So the address of source A is represented by N7 colon 0. Address of output is represented by N7 colon 1. Initially, I take 12 as a input to the source A. So 12 is represented in form of binary, as I already explained to you. It represented by 1100. So initially when TOD doesn't get supply, the output is represented by 0. You can see in the data files the output is 0, that is N7 colon 1 is equals to the 0, right? So when we supply to the TOD instruction by switch I colon 0 slash 0 by 1 or changing their state by normally open to normally close, you can see my output is changed, and you can see the data files, the output is changed by 00010010, right? Or in form of decimal, you can say the 12 is represented by 18 in form of BCD. But BCD is a binary number, so it represented by in form of binary, that is 00010010, right? Just because of explanation, I just converted to the output in form of decimal. That's why you can see here 12 is a input and 18 as a output. But actually the BCD represented in the binary, so the final output is obviously it's 00010010, right? Next instruction is FRD instruction, that is convert from BCD. TOD is convert to BCD, FRD means convert from BCD. So initially in this case also you can see in the diagram, FRD also takes one input and provides one output. One input in form of source and one output in form of destination. So address of source I provide is N7 colon 0 and the destination address is represented by N7 colon 1. Here I provide 18 as a input. You can see in the data files the source value of source A is 18, but here you can see in the FRD instruction the source value is represented by 12H. Don't get confused, but 12H is a representation of hexadecimal. 18 represented in hexadecimal by 12H. 12 doesn't mean that 12 in decimal, right? I provide 18 in decimal, or you can say 00010010 in binary, or 12H in a hexadecimal. So input is 18 in form of binary, it represented by 00010010, or in form of hexadecimal it represented by 12H. So initially the output is 0 and input is 18. Clear? When I provide supply to my FRD instructions by the switch I colon 0 slash 0, it provides the output to the address N7 colon 1 in form of 12, or in form of binary. You can see in the data files 00001100. In the diagram you can see the both type of representation, decimal representation and binary representation also, right? So when the input is 18, it converted to the 12, or when 12 is an input and it's converted to the 18. So 12 in a decimal represented by 00001100 in binary, and in BCD it converted by TOD instructions 00010010, And when we provide 18 in FRD, means 0001010, it changes to 12, means 00001100, right? Next instruction is related to the gray code. So first I'll explain the what is gray code, then we will see the instructions. The gray code, also known as the refracted binary codes, is a binary number system where two successive values differ in only one bit. This property minimizes the chance of error during the transition from one value to another, making gray code particularly useful in digital system where errors can occur due to slight change in voltage or timing. Key characteristics of the gray codes are 1-bit changes. Each successive number in gray code differs from the previous one by only 1 bit. Second characteristic is error minimizations. By ensuring only 1 bit changes at a time, the chance of error during transition between values is reduced, which is why gray code is often used in applications like position encoders. Converting binary to gray codes, the first step is the most significant bit, that is MSB of the gray code, is the same as the MSB of the binary number. The step 2 is for each subsequent bit performs an XOR operations between the current binary bit and the previous binary bit. Let's take the example to convert the binary number 1011 to the gray code. The first step, the first bit of gray code is equals to the first bit of binary, that is equals to 1. In the second step, the second bit of gray is equals to the second bit of binary, that is 1. XOR is XOR to 0, that is first bit of binary, and finally we get 1. The second bit of gray is 1. The third bit of gray is equals to the third bit of binary, that is 0, with XOR of 1, that is second bit of binary. So ultimately we got 1 as a third bit of gray. Similarly, fourth bit of gray is equals to the fourth bit of binary, that is 1, with XOR 0, that is third bit of binary, and ultimately we got 1 as a fourth bit of gray. So finally 1011 in binary is represented by 1110 in gray code. Converting gray to binary, first we convert binary to gray, and second we convert gray to binary. For this, the first step is the most significant bit of the binary number is the same as the MSB bit of the gray code, and the second step, the each subsequent bit performs an XOR operation between the previous binary bit and the current gray code bit. Let's take an example to convert gray code to binary. The gray code is represented by 1110. So the first step is the first bit of binary is equals to the first bit of gray, so it is represented by 1, and the second bit of binary is 1. We are using the first bit of binary and XOR of 1, that is second bit of gray, so ultimately we are getting 0 as a second bit of binary. Similarly, for the third bit of binary, we are using 0, the second bit of binary, with XOR of 1, that is third bit of gray. So ultimately we are getting 1 as a third bit of binary. Similarly, the fourth bit of binary, we are using 1 for the third bit of binary and XOR with 0, that is fourth bit of gray, and ultimately we are getting 1 as a fourth bit of binary. So ultimately 1110 in form of gray is converted to the 1011 in form of binary, right? The conversion, as you can see in the diagram also, the simple way how to convert binary to gray and gray to binary. right? Let's take the view and the programmable view. Here you can see my GRD instruction is connected to the switch I:0/0, right? It also take one input in form of source A and also provide one output in form of destination. Destination address is represented by N7:1. This output instruction converts the gray code source to integer and place it in the destination. On a true run, the instruction set the value of the destination to the integer value corresponding to the gray code source. If the gray code input is negative, high bit set, the destination is set to the 32767 and the overflow flag is set. The GCD instruction only operates on word operands. Entering parameters, the source contains the gray code input. This may be a direct or indirect addressing using any O, I, B, T, C, R or N data files. Destinations contain the integer value corresponding to the source. This may be a direct or indirect addressing using O, I, B, T, C, R or N data files. O represent the output, I represent input, B represent bit, T represent timer, C represent counters and N represent normally N bit, right? The arithmetic flag S:0/0 carry bit is reset, S:0/1 overflow bit reset if the gray code input is negative, otherwise reset. S:0/2 0 bit reset if the destination bit is 0. S:0/3 sign bit is reset, right? The math overflow trap bit is only set if the overflow bit is set, otherwise it remains in its last states. So that's all for this lecture. In this lecture we covered the mathematical instruction in PLC programming. In the next session we will explore more application based PLC programming. Thank you. Happy learning.